It may sound crazy, but have you ever imagined the end of the universe? Not the end of the Earth or the death of the sun, but the true end of everything. Space, time, energy, and matter? Will our universe freeze forever in absolute silence, or will it collapse violently, crushing everything back into a singular point? These two scenarios, the big freeze and the big crunch, are some of the most fascinating and haunting possibilities posed by modern physics. In this article, we will dive deep into the nature of these two endings, explore the scientific basis behind them, look at lesser-known but thought-provoking theories, and raise intriguing questions about the true nature of the universe. Get ready for a journey where time becomes flexible, space may shrink, and the future of all existence remains an open mystery. The current picture of the universe, the expanding universe. It may sound simple, but the fact that the universe is expanding is much more than galaxies moving away from each other. It is a profound cosmological event that reveals the long-term future and ultimate fate of everything. Edwin Hubble's discovery in 1929, that the farther away a galaxy is, the faster it moves away from us, led to the concept of the Hubble constant, a measure of the universe's expansion rate. However, this expansion is not like objects moving through space. In reality, space itself is stretching. As light travels through this expanding space, its wavelength also stretches, a phenomenon called redshift. This not only confirms that the universe is expanding, but also provides us with a cosmic clock. The light from more distant galaxies is older, showing us the universe in its earlier stages. One less talked about fact is that this expansion is not uniform everywhere. Because matter is unevenly distributed, some regions of space expand slower or faster than the average. Some cosmologists suspect this may be evidence of superstructures or hint at the existence of a multiverse, where different bubble universes expand at different rates. An especially fascinating question arises: could we be living in a special region of the universe, one where expansion happens just right for life to exist? If so, perhaps our existence creates a kind of observational bias, what scientists call the anthropic principle. The shocking discovery by Edwin Hubble in 1929 that galaxies are moving away from each other overturned the old idea of a static universe, an idea Einstein once tried to preserve with his cosmological constant. Accelerating expansion and dark energy. At the end of the 20th century, an unprecedented breakthrough in cosmology occurred when independent research teams discovered that the expansion of the universe is not just continuing but accelerating. This conclusion was drawn from observing type Ia supernovae, standard candles that serve as very accurate distance markers in the universe. This accelerating expansion was shocking because before this, it was believed that gravity from matter in the universe would gradually slow down the expansion. Instead, a mysterious repulsive force took over, causing space to expand faster over time. This mysterious force is called dark energy. Dark energy is not matter or radiation, but a form of energy inherent to space itself, with properties that counteract gravity and increase the expansion rate of the universe. Today, dark energy makes up about 68% of the total energy in the universe, making it the dominant component. An interesting and less discussed aspect is that the true nature of dark energy remains one of science's greatest mysteries. Some theories suggest that dark energy may not be a fixed constant, like Einstein's cosmological constant, but a dynamic field that can change over time and space, such as quintessence. If this is true, the nature of dark energy could evolve, leading to different scenarios for the universe's future, from eternal expansion to collapse, or even a big rip that tears apart all matter. Additionally, dark energy is closely linked to the concept of quantum vacuum energy, where the lowest energy states of quantum fields in space might act as a source of dark energy. This complexity makes the study of dark energy an interdisciplinary field connecting particle physics, cosmology, and field theory. In summary, accelerating expansion and dark energy not only revolutionize our understanding of the universe, but also raise deep philosophical questions about the origin, nature, and ultimate fate of all matter and space. Big Freeze, the cold death of the universe. Definition of the Big Freeze. The Big Freeze, also known as heat death, is the scenario where the universe continues expanding forever at an accelerating rate. As a result, the density of matter and energy steadily decreases, and thermodynamic processes move toward maximum equilibrium. Entropy reaches its peak. In other words, the universe will become too cold and too sparse to sustain any organized physical processes. No new stars will form. Old stars will gradually die out. Black holes will evaporate through Hawking radiation. Eventually, the universe will be left as a cold soup of fundamental particles drifting through infinite space. The physical basis and supporting evidence. Accelerating expansion, confirmed by observations of Type Ia supernovae and the cosmic microwave background, CMB. Dark energy. If dark energy is a constant, like the cosmological constant lambda, the universe will continue expanding forever. Entropy principle. According to the second law of thermodynamics, entropy in an isolated system always increases. The universe, in essence, is such a system. Lesser-known facts about the Big Freeze. A colorblind universe. At some point, all galaxies beyond the Milky Way will become invisible because they move away so fast that their light will never reach us. The degenerate era. After about 10 to the power of 14 years, only white dwarfs, neutron stars, and black holes will remain. Black hole evaporation. Over extremely long timescales, around 10 to the power of 100 years, black holes will evaporate due to Hawking radiation, leaving a completely empty universe. Is the Big Freeze really cold? The death described by the Big Freeze is not simply about coldness. It is about absolute isolation of information. There will be no interactions, no light, no radio waves, no way to transmit information. Existence becomes meaningless. Big Crunch, the reverse death. Definition of the Big Crunch. The Big Crunch is the scenario opposite to the Big Freeze. Instead of expanding forever, gravity or some other physical factor will overcome dark energy and reverse the expansion. The universe will start to contract, galaxies will move closer together, temperatures will rise, until all matter and energy are crushed into a single point. Conditions for the Big Crunch to occur. Critical density. If the density of matter, including dark matter, is greater than a critical value, gravity will be strong enough to reverse the expansion. Dark energy disappears or changes sign. If dark energy is not a constant but a dynamic field, such as quintessence, it may change over time and cause the universe to contract. Lesser-known consequences. A cyclic universe. Some theories suggest the Big Crunch could lead to a new Big Bang, the universe reborn in an endless cycle. Time reversal. There is a hypothesis that when the universe contracts, the direction of time itself reverses. Physics would run backward, entropy would decrease. A completely unfamiliar and controversial idea. Final fusion. Fundamental particles could merge at extremely high temperatures, leading to a primordial plasma state, a replica of the universe just after the Big Bang. Comparison and discussion. The Big Freeze and the Big Crunch are two completely contrasting scenarios for the future of the universe. Each is based on different physical hypotheses and leads to profoundly different outcomes. The Big Freeze occurs when the universe continues to expand endlessly under the influence of dark energy. Matter and energy densities become increasingly dilute. Physical systems move apart and can no longer interact, and entropy steadily rises toward its maximum. The temperature of the universe drops close to absolute zero Kelvin, and all organized biological and physical processes gradually cease. In contrast, the Big Crunch is a complete contraction. If gravity becomes stronger than dark energy, or if dark energy changes in a way that does not support expansion, the universe will slow down, stop expanding, and begin to contract. Galaxies move closer, temperatures rise, and eventually all matter is compressed into a singular point. This scenario represents a chaotic end with extremely high density. Regarding entropy, the Big Freeze predicts a continuous increase leading to maximum thermal equilibrium and maximal disorder, while the Big Crunch could potentially bring about a decrease in entropy if time truly reverses, an idea still debated within the scientific community. Temperature-wise, the Big Freeze approaches near 0 K, a state close to absolute freezing, while the Big Crunch reaches extremely high temperatures, a fiery state similar to the Big Bang. Finally, the structure of matter in the Big Freeze gradually breaks down, with galaxies and stars becoming isolated and fading away, whereas the Big Crunch ends with all matter crushed into a single point with no distinct structure remaining. The timeline for the Big Freeze could span trillions of years into the future, while the timing of the Big Crunch remains uncertain, depending greatly on the nature and evolution of dark energy as well as the matter density in the universe. Both scenarios are not just physical hypotheses, but also raise profound questions about the nature of time, space, and the existence of the universe itself, opening many avenues for future research and philosophical reflection. Other strange scenarios. Big Rip, the Great Tear. The Big Rip is an extreme and terrifying scenario about the future of the universe, based on the hypothesis that dark energy not only sustains expansion but also grows stronger over time. In this case, the expansion not only continues but accelerates at an ever-increasing rate, surpassing the gravitational force that holds objects together. As a result, the expansion causes the distance between objects in the universe to grow so rapidly that even the strongest bonds cannot hold. First, galaxy clusters will be torn apart. Then the galaxies within each cluster will disintegrate. Next, star systems will be stretched, planets and moons will break apart, and finally, even atoms themselves will be ripped into fundamental particles. A lesser-known fact is that in the final stages of the Big Rip, not only matter but the very fabric of space and time is severely distorted. Space stretches infinitely, and time may lose its meaning in ways that modern physics cannot fully describe. In other words, this is not just the destruction of matter but the disintegration of space-time itself. Based on calculations of the increasing rate of dark energy, the Big Rip could occur within several tens of billions of years, a very long time but not infinite. If this scenario comes true, it will be an unavoidable ultimate fate of the universe and a major challenge for scientists trying to uncover the true nature of dark energy, the factor that decides the universe's final destiny. Vacuum decay. Vacuum decay is one of the most frightening and less discussed scenarios regarding the end of the universe. This concept originates from quantum physics and relates to the false vacuum state that our universe might currently occupy. In physics, vacuum is not simply empty space, but the lowest energy state of a quantum field. However, multiple vacuum states with different energy levels can exist. A truly stable state called the true vacuum, and a temporarily stable one called the false vacuum. If our universe is in a false vacuum, it means it is not in the lowest possible energy state. Vacuum decay occurs when a small region of the universe transitions from the false vacuum to the true vacuum. This region forms a bubble of true vacuum with lower energy, which then expands at the speed of light. Wherever this bubble spreads, it radically changes physical constants, fundamental interaction laws, and the structure of space-time in that region. This phase transition can destroy atomic structures, fundamental forces, and completely distort the existing universe, making life or matter as we know it impossible. What's more terrifying is that this process could happen suddenly, without warning, and independently of the universe's expansion or contraction. It is an event entirely beyond human control and could occur at any time. The vacuum decay scenario not only shakes the foundations of physics but also raises profound questions about the stability of reality and the nature of the universe. It serves as a serious reminder of the uncertainties and mysteries that modern physics has yet to solve. Inhomogeneous heat death. Inhomogeneous heat death is a lesser-known hypothesis offering an interesting perspective that the thermal death of the universe might not happen uniformly across all space. Instead of a cold, silent death spreading evenly everywhere, some regions of the universe may reach thermodynamic equilibrium, maximum entropy, sooner than others. This idea is based on the fact that the universe is not perfectly homogeneous. Physical conditions like matter density, dark energy, temperature, and interaction forces can vary from region to region. Therefore, some areas might die faster, becoming extremely sparse and cold, while others may remain vibrant, with active stars and galaxies, for much longer. A special consequence of this hypothesis is the coexistence of regions of the universe evolving at different thermodynamic stages. This suggests that we might be living inside a bubble of the universe that has not fully reached heat death, while other regions outside have fallen into eternal silence. This hypothesis paints a more complex picture of the vast universe, where not every part evolves synchronously at the same rate, creating strange diversity in the universe's final stages. It also enriches the theories of the multiverse, where each bubble or universe region might have its own physical laws and evolutionary history. Thus, inhomogeneous heat death is not only a fascinating scientific possibility but also challenges how we imagine the end of everything. A process that is not simple or uniform but potentially a complex, multidimensional, and infinitely extended transformation. Conclusion: how will the universe end? We still do not have a definite answer. Current theoretical models are based on incomplete observations and rely heavily on the nature of dark energy, something we barely understand. However, proposing scenarios like the Big Freeze or the Big Crunch is not just an intellectual exercise. It is how we confront the biggest question. What is the true nature of the universe's existence? Does it have a beginning and an end? In this journey of exploration, every physical clue, every astronomical observation, and every equation is a piece helping humanity to assemble a vast picture, not only of where we live but also of the ultimate fate of everything that has ever existed. So, what do you think? Will the universe die in absolute cold or collapse into a single point? Share your thoughts. Who knows, one day you might be the one to lay the first stone in unlocking the universe's final secret.